The typical machine learning algorithm is starved for data. While techniques like one-shot learning, transfer learning, Bayesian priors, and many other methods help us cope with the lack of data, nothing is as satisfying after a long day skiing down the gradient descent slopes as a large glass of well-labeled training data. This is Data Skeptic Consensus, and the 18th installment in our series about how multi-agent systems achieve collective decision-making. The appetite for labeled data and a hope that there's a wisdom in the crowd have sent many researchers on a path to crowdsourcing data labeling. Today on the show, I speak with Omkar Ranadive and Suzan about their recent work applying machine learning to crowdsource data from Earthquake Detective.
I'm Omkar Ranadive. I'm a second-year master's student at Northwestern University, and I'm collaborating with the Earthquake Detective team as part of a part-time researcher at Sierra.
Hi, I'm Suzan. I'm a professor in the Department of Earth and Planetary Sciences at Northwestern University. I am also a research advisor and instructor in the IDEAS project, which is an NSF research traineeship, where graduate students are also building citizen science projects and benefiting from the many volunteers that contribute to these projects. And I am the faculty advisor for Earthquake Detective.
Well, very exciting. And there's a paper I guess we'll focus a lot of our discussion on today that came out somewhat recently, applying machine learning to crowdsource data from Earthquake Detective. So a couple things I want to unpack there. Maybe let's start with Earthquake Detective. What is that?
Earthquake Detective is a crowdsourcing project which is hosted on Zooniverse platform. So basically, Zooniverse platform is a place where people can host their own crowdsourcing projects, and then volunteers all around the world can classify the data in these projects. So in Earthquake Detective, we essentially give users seismic signals to classify, and so the users are shown a plot and an audio file, and based on that they perform their classifications.
And where does the data come from? How is it generated?
So this data is basically freely available, and the way we download it is using a tool called as OpSpy. So it's a Python-based library. Using OpSpy, we can collect data from different earthquake stations all around the world.
And so I imagine most listeners have probably seen those plots of seismic data, sort of the line chart. Could you go into a little bit more detail about what exactly that is? Like, it's easy to read the magnitudes, but what's the actual measurement that takes place to get us that data?
Basically, we actually download the raw seismic signals using OpSpy, and then we filter the data, and then it's plotted, and then we also create a sped up version, which is that audio file. And so the actual seismic data is like around 30 minutes long, and the sped up audio version is around 5 seconds long. So what happens over here is this data is representing a special class seismic events, which are called as potentially triggered seismic events. And so basically, what are these potentially triggered seismic events? Whenever a large magnitude earthquake happens somewhere in the world, it may cause some local seismic events all around in different parts of the world. And so the reason we are interested in these specific events is because they have certain characteristics. Like, these local events are difficult to classify because they have low magnitude, they are narrower in bandwidth, and they can occur at any time during the surface wave duration of the larger event, which is like 30 minutes. So you can see that all of this makes it difficult to classify it. And so that's why we provide it to the volunteers in the form of a plot and an audio file. And so the reason it's easy for volunteers to classify it without having any prior knowledge about seismology is because these seismic events have specific characteristics. So for example, an earthquake signal in a plot, there would be a spike, and that's basically signifies a quick release of seismic energy. And in terms of audio, it sounds like someone is slamming a door. And then for example, the other kind of seismic event we have is a tremor. So this, in the terms of plot, looks like there are multiple smaller spikes in the signal. And in terms of audio file, this sounds like a train moving on a railway track. And on the other hand, we have noise, which has no distinguishable characteristic.
Could you give us some samples of what these audio clips sound like?
Yeah, sure.
Yeah, so I wanted to say that where the data come from is amazing because there's many seismic networks around the world, but also in North America. And we have chosen to focus on seismic data from seismic networks in North America. And the operators of these networks are a variety of people, but the largest one of which is US Array from the EarthScope research program. And all seismic network operators have generously made all of their data open and free to anybody who would like to have it. And so there's an organization of universities that has collaborated to form, for example, a data center, right? An organization that has a data center. And all of that data from US Array and all these other cooperating seismic networks from Alaska and all over the other US states are in this IRIS Data Management Center that provides data services to anybody. And so that's where the data are coming from. And like Omkar said, we're using OpSpy to access that data, but there are multiple other ways in which people can access that data.
And roughly speaking, how much data are we talking about, both in terms of how many years they've been measuring for and maybe how many events they're capturing per year? How do we measure this data set?
So US Array has been operating for nearly 20 years, and it was probably the most massive seismic network that's ever been designed and operated. But all of the other networks have been operating as digital networks, providing data for many more decades, since the 80s or 90s in some cases. Some of the networks are temporary, but most of our data are coming from EarthScope's US Array.
So I would like to add to that. So while the data is huge, what we are interested in is in that subset of data, which is also classified by our volunteers on the Earthquake Detective platform. So that is roughly 130,000 samples. So we download the same amount of data and provide it with a label based on the labels which were given by volunteers.
Could you share maybe a description of what that experience was like for a volunteer? What steps did they have to do?
Okay, so it's actually pretty much like a game-like interface. So like I talked about this previously, the volunteers are shown a plot and an audio file, and it's pretty simple to classify it based on that characteristics which I just talked about. So it's a game-like experience, and I think it's pretty fulfilling for these volunteers because they get to take part in actual research and they are getting involved in science. And the reason I say that it's actually the volunteers are actually having fun because there are actually pretty fruitful discussions happening on the forum of Earthquake Detective. So the volunteers like pick out specific samples and say, hey, how does this sound like? Is this actually an earthquake? And so on. It's pretty interesting to see that people are getting interested into science using this.
Can you, and we'll ask again at the end, but maybe share a link or what someone should search for if they want to be a volunteer?
Pretty simple. So you can just Google Earthquake Detective and it should be the first link in Google, and you can create an account over there and you can just start labeling samples. But just to add to that we have put the project currently on pause because we are analyzing the data, but we will have it up shortly up again.
And that process, I would assume most of your crowd workers don't necessarily have the right academic background per se. How long does it take them to start giving useful responses? Is there any training or learning curve to it?
Yes, so we have a few practice examples which are given to them, and then we kind of like give them very basic training based on that. And we also have explanations of how earthquakes are supposed to sound, how tremors are supposed to sound, and so on. But this is actually a real problem, right? So despite all this, there are going to be volunteers who won't be able to classify it well. There are going to be volunteers who will be able to classify it well. So what we are trying to incorporate now is to score the volunteers, basically give them a reliability score, because we need to incorporate this reliability score while applying machine learning algorithms to it, right? Because otherwise the labels cannot be guaranteed to be correct. So we need to take that into account while we are training our ML algorithms.
Roughly speaking, how many class labels are you interested in?
On the platform, there are 4 labels over there. So one of them is earthquake, noise, tremor, and none of the above. So basically the first 3 are obviously quite obvious, and none of the above label is because, like I talked about before, events are pretty difficult to detect. So even for seismologists, it's quite difficult sometimes to like give them a proper category. So if volunteers are unsure about what that label might be, they just give none of the above. But while training, we have only included the first 3 labels, which is earthquake, tremors, and noise, to keep things simple and to not add a lot of variance.
I guess I don't really have a baseline expectation. What does a crowdsourced worker, in terms of accuracy, how do they perform? And maybe if you know it in contrast to what a grad student who's been looking at this for a while yet, what is the ceiling of accuracy on this imprecise classification task?
The way we actually do this is, first of all, we create a golden set, which is made by our seismologists. So the data on earthquake detective is not only classified by volunteers, but also by some of our seismologists, right? So the data which was classified by our seismologists is what we use to create a golden set. And then this set can be used to test how well that ML algorithm is performing. So one really cool result which we found was that during training, we included the data from volunteers, and as expected, the accuracy wasn't too high. It was around 80%. And this is expected because there is variance in the data, right? Like some of the labels might not actually be true. But then when we tested the same algorithm on this golden set, which is set labeled by a seismologist, it gave a 90% accuracy. So this kind of shows that even though there is variance in the training data, the algorithm in the end managed to learn useful representations.
So you gave your crowdsourced participants the audio clip and the visual in terms of the data visualization of the measurements. What did you give your machine learning algorithm?
For our machine learning algorithm, we did something similar. So there are two aspects to it. So the first aspect is we take that seismic signal and then we apply a wavelet scattering transform to it. So in simple terms, what this is, a wavelet scattering transform has a family of wavelets, and each family of wavelets is basically taken and we convolve it with the signal, and then we get an output. I think before going into this, I think I have to talk a bit about why not just use the generic convolution architecture, right?
Sure. Why not the raw data?
Yeah. So even though we have a lot of the data, like I talked about previously, this data has a lot of variance in it. So if we just throw everything into it, it will not give a good result. So what we have to do is take a subset of the data which has a lower variance in it. That is, take the data which is classified by fairly reliable volunteers. But now that the data is lower, the standard deep learning techniques don't work that well, right, on small data sets. So something like wavelet scattering transform works really well because it is made up of predefined set of filters. So you don't really need training for it. So we use this predefined set of filters to convolve with our signal, and this gives us some representation of that signal, and which is passed into a fully connected network. But this is just one aspect of it. The other aspect is, just like how we are showing plots to volunteers, we give 3-channel plots to the machine learning algorithm, and the algorithm also uses that to, and then we simply apply image convolution, and then it combines both these features to classify. So just to add to that, when I talk about 3-channel plots, it's not RGB plots. It's basically grayscale plots, but in 3 different seismic channels. So what I mean by that is the earth rotates in 3 dimensions, right? So similarly, the seismograms record the data in 3 different directions. And so we provide the algorithm with the info of all these 3 directions.
I suspect the application of deep learning to this problem is one of the novel things you've done. I don't know if you were the first, but you may have been. But you probably weren't the first to think of wavelets as a solution. Maybe historically people were doing that for some sort of feature engineering. Could you talk a little bit about what was inspired by existing techniques and what was novel in the work?
The novel part about this is that no one has really worked on PT seismic events. So that is the potentially triggered seismic events. So all the techniques we actually used were used in some form on other data sets or other forms of signals, etc. But on potentially triggered events, no one has really applied machine learning on a proper scale. So that's what we have done. And yes, like you said, wavelet scattering transform have existed since a long time, but I think they have died down in popularity lately because of that end-to-end architecture of traditional convolutional neural nets. But I think they are still pretty useful, as we actually saw in our case, if used properly.
Thanks to this week's sponsor, Brilliant. Brilliant's a longtime sponsor of the show, and I hope by now you've all checked out their awesome platform. It's a great learning tool. They've got these really excellent courses and learning paths, and even the problem of the day that can help keep you sharp. I do spend a little time on Brilliant every week, and lately I've been going through, I announced this a couple, months ago, and I just saw this was in preview. Out now, the quantum computing course. I'm very excited to dig into that and report back later on how I'm doing. 33 interactive quizzes, 395 plus concepts. Learn to build quantum algorithms from the ground up with a quantum computer simulated in your browser. And I saw some of the demos for this. It is a fun, interactive thing, just like all the courses on Brilliant. If you're interested in quantum computing, you definitely need to go check that out. There's a fun way they're building quantum circuits. But if that's not your cup of tea, perhaps Introduction to Neural Networks or the Logic course are for you. There's something for everybody and maybe even for the whole family over at Brilliant. So head over to brilliant.org/dataskeptic. That code will get you 20% off a year of Brilliant Premium. So head over to brilliant.org/dataskeptic. I don't know if you had a chance to connect directly with any of the crowdsourcers or if maybe you tried it yourself, but I'm curious if you have any guess or intuition about the features that those users are using. In other words, do humans classify in a different way than machines do for this problem?
So for normal volunteers, I think it's just about hearing the sound, right? So they are going to hear that characteristic sound over there. Is it slamming of a door? Does it sound like a train moving over a railway track? So you might argue that we are doing something similar to what machines do, but I think machines are able to extract information at a much deeper level. For them, it's not about the sound of a slamming of a door. They're actually able to extract relevant frequency information from the signals and classify it. So I think that's also an advantage of using a machine learning for this, because after performing machine learning, we can provide that data to proper seismologists. You can do better analysis on it.
And that 130K sample size, that's a good number of samples, but not the biggest data set I've ever heard of. Did that pose any challenges for you, in particular with the deep neural network architecture, which is generally very hungry for data?
Yeah, definitely, it did. But that's kind of why we use the wavelet scattering transform to avoid some of the issues.
I'd also a little bit curious about how a collaboration like this gets started. I don't know Northwestern in particular, but in my experience, the Department of Earth and Planetary Science isn't necessarily co-located with the Computer Science Department. How did you guys get connected?
Basically, what happened is I'm obviously very interested in applying machine learning to different fields of sciences. And so we have Sierra, which is a Center for Interdisciplinary Research in Astrophysics. And so I contacted them, like, is there any researcher position which I can work on part-time where I get to apply machine learning algorithms to cool stuff? So I got in contact with them, and basically they are affiliated with this earthquake detective project. And so we got together that way.
And Suzan, maybe I could ask you specifically, what is your perception with your background about machine learning? From the people in the community of machine learning, we have the perspective that we're going to come fix everybody's problems in every field. What was sort of your understanding going into it?
Oh, well, yeah. So machine learning is very popular and looks really promising. But at the end of the day, you need really good data sets for training, right? And so that requires the time of experts to look at all the data and to put it in the proper format and maybe do a wavelet transform on it and see what that gives. And then basically label them in responsible ways. And so I think there's definitely a two-way street here where you need expert input for machine learning to work properly, but you also need machine learning expertise like Omkar is bringing to apply this analysis to so many data that no individual seismology expert can actually analyze by themselves.
Yeah, it's definitely an interdisciplinary approach, I would say. You have to have some of both fields. But the crowdsourcing kind of is very interesting in a way. Maybe it could be useful if the crowd learners could do some basic filtering so that the more advanced people in reading seismology plots could look at only 1 in 100 plots or some sort of pipeline like that. I guess, do you guys have a vision for how your work will maybe improve this sort of classification in the future?
Yeah, so I think one way we can do this is you could think of this as a cyclic loop. So volunteers are classifying something. Based on those classifications, we are training our ML algorithm. And after a point, our ML algorithm gets good to some extent, right? And then, but still there would be some samples which that ML algorithm won't be able to classify well. So we can, depending on how badly the ML algorithm is classifying those specific samples, we can forward them to seismologists who are experts at classifying. But if the ML algorithm is able to classify it to, let's say with 70 or 80% accuracy, we can give it to someone with an intermediate level of skill set. So we can divide the samples on different sets of people with different sets of skills.
I'm also curious, given the underlying data set, Suzan, you were describing some great properties of it, that it's open and everyone's kind of sharing and contributing, but more data also means more variety of data and more maybe different types of manufacturers who made the sensors that measured it. Does that amount of heterogeneous data make this extra challenging, or is it just worth it to have all the extra data?
It's definitely worth it because obviously we take some of these instrumental responses into account when we pre-process the data before they go into a machine learning algorithm or before they are presented to volunteer scientists, like we have with Earthquake Detective. And so we take it into account and we translate the data as much as possible to physical units of ground motion and also limit the bandwidth so that we know that instruments that we're using the data from all have sensitivity in that bandwidth. And it's really useful to have the volunteers look at some of the more complicated data that we haven't trained the algorithm in, right? Because the volunteers can then classify things as none of the above, and then we can actually analyze that data and see, well, can we make a new category of some of the events in that data and then get some more input from volunteers and then train our machine learning algorithm to also recognize that new category of data.
I'm curious if, in the same way that the data can be shared amongst collaborators, is there a plan for the model to be shared, or how can this insight be democratized in certain ways?
Yeah, certainly. So our entire project is open source. It can be accessed on GitHub. And I think, yeah, that's the idea. Like, use our tech. And I'm pretty sure that this techniques which we have applied can be used for detecting other kinds of seismic signals which are not potentially triggered. So certainly. And in fact, we are also planning on using techniques which other people have used for detecting other kinds of seismic signals into our project.
I think that Omkar is very right in that whenever there's small amplitude, short duration signals that seismologists are interested in for one or another reason, and there are many reasons I can think of why seismologists are interested in these sort of weak signals that are hard to detect. And so any seismologist that would like to use this platform of Earthquake Detective can contact us, and then we can feed the data that they're interested in into the platform and have both volunteers and maybe the machine learning algorithm as well have a look at them and help classify and pre-filter them like you suggested earlier.
So there's a lot of benefits to a system like that purely from the research and understanding our planet point of view. But I'm curious if you guys have any way of relating this to our everyday lives. I'm a resident of Los Angeles, California, not too far from the San Andreas Fault, so earthquakes are sometimes on my mind. Is there a measurable benefit or a warning system that could emerge or be improved as a result of efforts like this?
Yeah, so definitely, right? Because large earthquakes are luckily rare, but the smaller you go in earthquake magnitude, the more of them occur. And so if we can study the tiny earthquakes, because there's so many of them, then we can actually learn things about the larger earthquakes through the scaling laws that exist. So the more of the small earthquakes that we can study, the better we'll eventually understand the larger earthquakes that cause damage and that you need to worry about. I hope you have an earthquake kit in your basement and that you know about drop, cover, and hold on.
I do, but good to note, so thank you for the reminder. I should check on that kit as well. That probably needs a good annual checkup too. Well, one of the novel things that I took away from the paper was in how you could slice and dice the training data in light of the different crowdsourced data you had. So there were these groups where you could train on just the clean data, or train on the clean data plus the gold standard data, or clean plus gold plus all volunteers. Could you share a little bit about that split and what maybe you thought you'd find with those breakdowns and actually how those benefited the model or not?
It was more about whether the techniques we are using are actually working or not. So the best way to do that is to first train on the cleanest data available. So the clean data is actually not from Earthquake Detective, but it's very similar data which was filtered and labeled by a seismologist. So it's that perfect kind of data. So if you train on that and if the techniques which we are using are performing well on that, then it's like a proof of concept that those techniques actually work. So that was step one. And after we found that the techniques actually worked on that, and it did because we got a 95% accuracy on that, then we added in a bit more noise. That is data from Earthquake Detective, but labeled by a seismologist. So it has all those difficult characteristics which we talked about, but the labels would be accurate. And then when it worked on that too, then we added in a bit more variance. That is now data from Earthquake Detective, but by volunteers, which has further noise because it would be unreliable. So it was iterative process to make sure that the model is actually working at each stage.
Very nice. I like that as a form of validation. Well, I'm curious what comes next from both of your perspectives. This is certainly a nice model that has direct applicability, but where do you want to go in the future with this line of inquiry?
Basically, this model is not perfect, so we want to keep on researching more on this. So one is we want to try applying different techniques, maybe unsupervised techniques. So there are transformers are gaining a lot of attention. So what happens if we use attention mechanism for this? So a lot to do on the ML part, but also I think the important thing is on the reliability part. So we are using a subset of the entire data set. That is why we were able to get a decent performance. But when we include more and more data from volunteers, it's going to become more and more unreliable, right? So we need to somehow incorporate reliability scores into our algorithms better. So I think we need to work on that next.
Well, I know it's a practical hands-on problem, and there's certainly opportunities for people to contribute. If people are interested in this sort of thing, what might be some steps to getting involved? You'd mentioned that the source code's out there. People can certainly check that out. But what about students and things along those lines?
Yeah, so for those who just want to classify, obviously you can just go to the website, sign up for an account and do it. But we are also looking for project members for both seismologists or who might be data scientists or who just might be interested in computer science or earth sciences. So they can send us an email and we can get in touch because we are definitely looking for new members to join our project team.
Well, just knowing my audience, I suspect we'll find more data scientists than people with seismology background. But of course, if you overlap both, hit that email up. For those who are coming at this purely from a more mathematical, statistical point of view, but they're curious about earth science and things like that, could you talk a little bit about what the criteria you'd be looking for that would make a good lab member?
The bar is not actually too high because I managed to do it. I'm from the computer science background, and so I did not have any knowledge about earth sciences before that. But so I think to get a working knowledge about earth sciences is pretty easy. So like even if you have no knowledge of earth sciences but you're interested in learning, you can just join in and we can just talk about the basics and then get started with it. So
cool. And usually at a point like this, I like to ask, is there anything you think I should have asked about that we haven't touched on?
One of the things we noticed is that the volunteer scientists that have helped us enormously with these classifications that they've done, that are now being analyzed in research contexts, a lot of them liked participating in Earthquake Detective because of the sometimes crazy sounds that they get to hear, right? And then realizing this is the actual Earth that they live on that they're listening to. So partially in response to that, we have developed an app for iPhones that is called Earth Tunes. And this app is going to be available in the Apple Store, sometimes this week. And so basically people that download the app can select a place in the world, anywhere in the world, and then ask for a day and time and a duration, say 4 hours or 2 hours, and the data downloaded for them, and then they can listen to that. They can listen to the Earth speak.
Oh, that's exciting. And as this is coming out, that'll maybe be in the App Store. So iPhone users, take a look in the show notes and check that out. Well, Omkar, to wrap up, we touched a little bit on the model and specific next steps there, but I'm curious to get maybe if you have any thoughts or intuitions on where it could go. You'd mentioned transformers and the attention mechanism, which has been very promising in lots of other contexts, but those are also situations where there's kind of this Markov effect, right? Old data is of some importance. I'm not quite sure, maybe this is my just ignorance of the field. Is that also true with the Earth, or is earthquakes as unpredictable as I've been told they are from some people?
Okay, so I will first talk about this from a machine learning perspective. So the reason I talked about attention mechanisms is because we are trying to detect these potentially triggered events, which may occur at any of the time duration in that surface wave duration, which is like 30 minutes long, right? So attention mechanism might help us understand where that potentially triggered events are in that large 30-minute duration. So that's one aspect to it.
Yeah, that's very exciting. I think with that in mind, you have a strong case there.
And I think we got the idea for the attention mechanism, or at least I first heard about it, at the AI for Earth workshop at the NeurIPS conference. And I think there were some Stanford researchers that had used it successfully. So that was quite inspiring, at least for me. Omkar might have already known about this. But you talked about how earthquakes, unpredictable they are. And that's exactly the problem with earthquakes, right? We have no idea why they start when they do, or why they stop when they do. And that is a notorious, sort of hard to solve problem with earthquakes. And that's why there's a lot of seismologists investing time in at least developing early warning systems that can sense a P wave from an earthquake and warn people before the more damaging S waves and surface waves arrive. And so there's a lot of potential for machine learning in earthquake seismology.
Well, that's very inspiring to know, especially given that now it's such a great time to be getting into a field like this, and contributing in a way like that, which is very practical and actually tangibly saves lives, is very interesting and exciting all at once. Well, thank you both so much for coming on the show and sharing your work on this. It's a neat project, and I hope to see where things go next.
Thank you very much.
Yeah, thank you for having us.
That concludes this installment of Data Skeptic Consensus. Our guests today were Omkar Ranadive and Suzan Vanderlee. Claudia Armbruster is our associate producer, Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich.